Good morning. Welcome again to the video tutorial number 3, I suppose. This is the example for normal stress. I have on the screen right now the a member AC, which is a beam actually that is being hung using a rod AB, and the member AC is subjected to a vertical force of 3 kilonewton at a distance x from the rod AB, and we are asked to find what is the value of x, which is the position of that 3 kilonewton force acting on member AC from the rod AB. Now the condition has been set that we need to find the x of which the average compressive stress at support C is equals to the average tensile stress in the tie rod AB. So basically we need to determine what is the balance of that 3 kilonewton force in order for us to have an equal strength on support C and also rod AB. And we're also given what is the cross-sectional area for the rod, which is 400 square millimeters, and also what is the contact area at point C, which is 650 square millimeters. So let's go ahead and find out the all the forces acting on this one. I already have the okay, let me pull it out here, and okay, this is what is happening at member AC, where you have the force of C acting at this point here, and you also have with 3 kilonewton distance x, and we also have the force from the rod, which is denoted as FAB, and the distance is 200 millimeters. So this is basically the some of the free body diagram of the system, and in order to find out to solve this problem, we need to find out what's the internal loading at point A and point C, which means the FAB and also FC. And in order to solve for that, we need to do the equation of equilibrium. So let's go ahead and do that. Make it smaller a bit so it's easy to see. Okay. Now I'm going to do first off. Let's find out the equation of equilibrium. You have basically the summation of forces in the x is equals to 0, and you also have the summation of forces y is equals to 0. And we can also, since this member AC is in equilibrium, you can also do summation of moment at point A, that is also to 0. And okay, since x, there's no forces in the x direction, so we cross it out, and we do summation of forces in the y direction. So I have my FAB going up, then I have my 3 kilonewton going down, and I also have my FC. And this one is equals to 0. And this, I will call this as equation number 1. And similarly, I can also do the summation of moment at point A. Now, if I'm sitting at point A here, so all I can see is this moment of 3 kilonewton and also the moment generated by FC. And I don't have the moment coming from FAB because the FAB is running through the same line, the line of action through point A, and it does not have any moment arm. Okay, so let's go ahead and do the summation of forces, summation of moment at point A. So I will call this as positive. Now, if I'm sitting at point A, I will see my 3 kilonewton going the other way around. So I have 3 kilonewton, and that's my force, and times x, that is my moment arm. And I also have a positive FC, and the moment arm is 200 millimeter. And this is equation number 2. Now let's go ahead and try and solve this in terms of FA and FAB and FC. So I have FAB plus FC, and that's going to be 3 kilonewton. That is coming from 1. I'm just simplifying it, and I also have my 200 FC is equals to 3x. Okay, and this one is coming from number 2. This is from 2, and this is from 1. I'm just simplifying the equation so it looks better. So now what I can see is we have a relationship between FAB and also FC, and also a relationship between FC and also the distance x. Okay, now it says that the tensile strength, this is the condition, tensile strength at rod AB must be equals to the compressive strength at point C. So now let's go ahead and equate that. Okay, now first we find out what is the, sorry, this is not stress, this is not strength, this is stress rather. Okay, now I have at rod AB. Now if you take a look at rod AB, this is the area, which is 400 square millimeters, and I have my FAB going that way. So I can go ahead and find the normal stress attributed to the forces of AB at rod. AB is equals to whatever the force divided by the area. So in force is FAB, divided by, and the area for the rod simply is by, I'm sorry, it's just 400. Yeah. Okay, let's take it out. Okay, just divide by 400 square millimeters, and this is um, the tensile stress at rod AB. So I'm just gonna mark it in red so you can see it better. And simultaneously, you can also do the stress calculation at point C. Now we have point C and we have this is FC, and the area is, this is the same, you know, this is the area, it's 600, sorry, 650 square millimeters. So my sigma, which is my normal stress at point C, is also given by force divided by area, and that is FC divided by 650 millimeters square. So also going to indicate this in red. So now the condition says that the stress at AB and C is the same. So let's go ahead and equate these two, and we have FAB over 400 millimeters square is equals to my FC over 650 millimeters square. So this is the condition that satisfies that the stress at rod AB is equals to the stress at point C. Now let's go back and find out what is FAB from our equation here, and we have FAB plus FC equals to 3, since FAB equals to 3 kilonewton minus FC, and this is also coming from 1. And you also have so let's plug it in. So now I have 3 kilonewton minus FC, and what this one is actually FB, okay, divided by 400, and that's going to be FC over 650. So what we can do here, we can do a cross multiply. We can do a cross multiply. So I have my 400 FC is equals to 650 times 3 minus FC. I'm just going to omit the units for a while, and so I have 400 FC on this side, and I have 650 times 3, that is 1950 minus 650 of FC. Then I'm going to bring my FC on one side, so I'll have a common thing here. So I have 650 of FC added to 400. So I have 1050 of FC is equals to 1950, and my FC is equals to 1950 divided by 1050, and this will give you the answer in kilonewton. 1050 divide that, and I have 1.857 kilonewton, and this is one of the answer. From here, I will go ahead and try and solve for FB, since my FAB is, where's my FAB? Oh, okay. My FAB is 3 kilonewton minus my FC. That is coming from 1 just now. So my FAB is 3 minus 1.857, and that will give me my FAB, just sign that, 3 plus 1.048 kilonewton. Now, once we have that, we can go ahead and calculate what is the distance x, because we know from equation number 2 just now that, oh yeah, here it is. Uh, 3x equals to 200 FC, so that's 3x equals to 200 FC, and 3x equals to 200 FC. So my x is equals to 200 FC over 3, and my FC is 1.048 kilonewton, and divided by 3. So my x distance is 200 times 3. Did I miss something here? So I have, let's see, it's 200 here. It's 200, 1.048 times 3 divided. So I have my x at 69.87 millimeters. So this is my position of X. So basically, if we go back to the this equation here, this diagram here, you know that this the X. This is 69.87 millimeters. Okay, so this is the distance for X. In order for this system to be in equilibrium and you have an equal strength for this rod AB and also at point C. Okay, so that is the example for the problem that we have today. So I'm going to put this also in PDF so you can basically see it better than coupled with the video that I have here. So you can take the step-by-step approach of how we go about solving this. So till then, I'll talk to you later. Bye-bye. Okay, just a correction here. That is not 1.048 kilonewtons, but rather 1.143 kilonewton. So I go ahead and change that, and my X now is 76.2 millimeters rather than 69.87. Sorry for the mistake. Okay, talk to you later. Bye.